The birthday problem, or the birthday paradox as it is sometimes called, is a problem in probability theory, and this problem asks for the probability that in a set of n randomly chosen people, at least 2 will share the same birthday. So the problem is that if we have a set of n randomly chosen people, what is the probability that at least 2 among them have the birthday on the same date? And this probability can be calculated exactly, analytically. It's not a very difficult problem, but the result, the answer to this problem is not very intuitive. Even with a very small number of randomly chosen people, the probability of finding at least 2 people with the same birthday is very high. For example, if we choose even 23 people, say if we have a group of 23 randomly chosen people, and then in such a group there is more than 50% chance that at least 2 people in this group will have birthday on the same date. On the right hand side we have this graph which shows these probabilities. With around 60 people, 60 randomly chosen people, this probability is almost 100%. And this page also contains the exact calculation of probabilities. Here you can find how to calculate these probabilities exactly. It's not very difficult, but we'll not go into this. And here we also have a table which shows these probabilities for different number of people. So with 50 people, 50 randomly chosen people, the probability that at least 2 of them will have birthday on the same date is 97%, and with 60 people this becomes 99.4%. With 70 people it becomes 99.9%, and so on. So this result is not very intuitive because in a non-leap year we have 365 days. So it's not very intuitive that even with say 60 people, it's almost certain that we'll be able to find 2 people with same birth date. As I said before, this page also contains this exact calculation of probabilities, but what we'll do here is we will do this, check these results using numerical methods. Here I am using Julia language, and I've written this simple code. This is not very efficient, but I have written this in so that it is understandable. It's not difficult to understand, and it can be made efficient if one wants. So here I am using 2 packages, these plots, which is used for plotting in Julia, and this random package which is used for generating random numbers. So this first function, random birthdays, which takes an input n as integer, generates a list of n random birthdays. Here I am representing a birthday by the day of the year. So I'm just choosing a random number from 1 to 365, and for example, if I run this function for 10 birthdays, and this returns a list of 10 random numbers chosen from 1 to 365. Here the first number is 30, which represents 30th day of the year, and the second number is 37, which is 37th day of the year, and so on. So this function random birthdays generates a list of randomly chosen numbers from 1 to 365. Then we have the second function check same, which takes a list of numbers as input and returns true if in this list we have at least one repetition of a number, and returns false if there is no repetition. So for example, if I run this code with this list of numbers 1979, then it will return true because this number 9 is repeated. If I change this last number to 10 and again run this code, then this will return false because there is no repetition of numbers. So this check same function checks if a given list of numbers has a repetition. If there is even a single repetition, it will return true, otherwise it will return false. Then we have this third function which calculates the probability for a given number of people. Here n is the number of people and sample is the number of times we want to run this function in order to numerically calculate the probability. Here the default value of this sample value is taken to be 1000. We can change it at the time of calling this function. So for a given number of people, what this function does is it runs this loop for sample number of times. Here default value 1000. So if you do not give any other value of sample, it will run 10,000 times this loop, and in this loop it will first generate n random birthdays, and it will check if in this list of random birthdays there is a repetition or not. If there is a repetition, it will increase this number by 1, and if there is not, it will do nothing. And the probability will be simply the number of times it finds a repetition divided by the total number of samples. For example, if we run this function for n equal to 20 and take sample size to be 10,000, then we find that it calculates the probability to be 0.4153. Every time it will of course generate a different result because it depends on these random calculations, these Monte Carlo type calculations. So but if we increase the sample size, then this will converge to the exact known result. If we take a sample size of 1,100,000, then this gives us a result of 0.41157 for n equals 20. And on Wikipedia page, if we check the exact value of probability for 20 people, then we can see that this is 41.1%. And the numerically calculated result is 0.411. So it's very close to the exact known value. Now, since with these functions we are able to calculate probability for any given number of people, so we can plot this graph. We can calculate probabilities for different number of peoples from 1 to 100 and make a list of these probabilities probes, and then we can after generating this list, we can plot this list using this plot function. So we can get this type of graph of probabilities. On the x-axis we have the number of people, and on the y-axis we have the probabilities. So for 25 people we have this probability on the y-axis. These probabilities are probability for finding at least one pair of people with the same birthday. So this graph is generated by calculating numerical probabilities, and the analytic values are used in drawing this graph on Wikipedia. So this graph, as you can see, which is plotted using analytically calculated probabilities, is very similar to the graph that we have plotted using numerically calculated values. So this is how you can study this birthday problem using this simple code in Julia.